Okay, we have here today on the board another interesting integral. This one was suggested in the comments by Dan Dapp. We have the integral of this infinitely nested square root of x times x squared, x cubed, x fourth, on and on dx. Okay, now I did a problem really similar to this with an infinitely nested square root just a week or so back, and this one's gonna go about the same way. What I wanna do for my first step, I just wanna rewrite this and get it out of the radical notation. So like first we'll have x just under 1 square root. So I'm gonna write this as x to the 1/2. This x squared is under 2 square roots, so I can write that as 1/2 times 1/2, or we can write it as x to the 2/4. I'm not going to reduce anything at this stage, and then go into x cubed. We're going to have x cubed under 3 radicals, like 2 cubed is going to be 3/8, and then this is going to just keep going on and on like this forever. But then from here, what we notice is we're just multiplying all these terms with the same base x. So when we do that, we're just going to be adding the exponents. And we don't know what that is yet, but it's just going to be some number when we sum all these exponents up. So I'm just going to call this s. But the nice thing about this, when we find our s value, it's just going to be power rule, and we're going to be able to finish this really quick. So now all we need to do is just figure out what is this s going to be. Okay, now I've written out our series for s, just adding all these exponents. And now the first thing I want to check is, could this be a geometric series? So I'm just going to look at the ratio going from one term to the next. So if I look at what we're multiplying to get from 1/2 to 2/4, that's just going to be 1, because 2/4 is 1/2. But then for this term, it's going to be 3/4. And then for this term, it's going to be 2/3. So what we're seeing here is we don't have a consistent value between terms. We're not just multiplying by a single value. So this is not a geometric series. But now we notice, even though this is not a geometric series, it's actually really similar. There's a geometric series that we could look at as 1/2 plus 1/4 plus 1/8 plus 1/16. And then in this case, this is a geometric series because for each term, we're just multiplying by 1/2. And we have the similarity here between this and our series because we've got the same denominator here. So what that tells me is I think we can actually create a geometric series out of what we have here. So what I'm going to do from here is I'm actually going to split this up. So I'm going to write this, we have our first term 1/2. For this second one, I'm going to write this as 1/4 for the geometric series, but then we also need to add 1/4 here to get to 2/4. And then here I'm going to write this as 1/8 because we need that term. But then here we're going to have 2/8, so that we have 1 plus 2 gives us our 3/8. And we're just going to keep doing this on and on forever. But now breaking it out this way, all I need to do is just reorder my terms in order to pull out a geometric series, because we have our 1/2 times 1/4, 1/8. So we have our geometric series here with all these terms that start with 1 in the numerator. So all I'm going to do now is just reorder it so that we have our geometric series together. So now doing it this way, we've kind of created our geometric series. And when we have that, this is actually going to be easy to calculate because we have a formula for this. So I'm not worried about this part. Now this second part, we've got all these terms left over that we didn't circle here, the 1/4, 2/8, 3/16, etc. But now again, notice the similarity to our original s value that we want to find, because now the numerator is the same, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The only difference is the denominator. But what I can do is, if I actually factor a 1/2 out of this and rewrite this, well, now what happens is this is going to become 2, this is going to become 4, and I can fix all these. And so now by doing that, this piece right here under the blue, this is identical to our s value that we want to find. So we can just call this our s. So if this is the value of s, our original series, the thing we want to find here, and this is a geometric series that's easy to calculate, let's just use our formula for the geometric series to find this, and then we can finish this off. Okay, now we have our formula for the geometric series over here to the right, and we just need to know what is this a and r value that we're going to plug in here, but it's going to be a pretty simple calculation when we have it. So again, the r value is our common ratio. That's the ratio between these terms, and we just notice that it's going to be 1/2, so our r value is 1/2. We have to do this check on r that the absolute value of r is less than 1. Well, absolute value of 1/2 is less than 1, so we're good there. And then our a value is just our first term, so we're just looking for 1/2. So for this value, we just plug that in. Our first value is 1/2. We're going to have 1 minus our r value, 1/2. We end up here with 1/2 over 1/2, so this is going to just be 1. So coming back here, trying to find our s value. So our geometric series, the value that's just going to be 1. We have this 1/2 s that we found from the previous board. Just subtracting this 1/2 s from here, we're going to end up with 1/2 s equals 1, or our s value is going to just equal 2. So from here, all I need to do is take this 2, plug it back into our integral, and finish this off. Okay, so after doing all that series work, we end up with our integral of just x squared. So we end up with the simplest integral in the world, and we just have to finish it. We'll just use power rule on this, and we get our final solution of just x cubed over 3 plus c. Okay, good problem. Thanks again to DanDap. Thanks everyone for watching. Have a great day.